All right. First of all, thank you for the opportunity to speak. Very much enjoying the conference so far. Everyone can hear me okay? Yep, great. So yeah, I'll be talking about advancing Mamba models in PyTorch. Just a few topics to cover here. So first, what is Mamba? I'll explain at a high level what they are. Next, the whys. Why introduce something new to the ecosystem, and finally, I'll talk about IBM's work in advancing the state of Mamba plus PyTorch. So we've heard a lot about this. I know people are familiar, but just to recap, this is the typical model structure here. So we have some sequence of inputs, and there's repeating blocks of MLP, feed-forward layers, followed usually by attention, back and forth. And there's different rules of these layers, right? So the MLP layers, they just focus on each element in the sequence is processed in parallel. There's no cross-sequence information being passed around. It's the role of the attention layers to pass information in the sequence dimension. That's how you make causal. That's the causal nature of these models. What Mamba is it's essentially a drop-in alternative for the standard attention layer. It has two features that are nice. They're really prerequisites. One is that the training is super parallelizable. You can parallelize in the sequence dimension, just like transformers. And then the second reason, the reason why people are interested in Mamba is that inference is much better. It's faster and less memory intensive. And they're essentially a modern recurrent layer. So people might remember RNNs, the recurrent neural networks of the past. They're a better version of that. They were introduced by Albert Hu at Carnegie Mellon and Treadell, now at Princeton, of flash attention fame. I'm going to keep saying Mamba. I'm really talking about Mamba 2, but that's just a comment for the experts here. And essentially what you do is you scan in some way over the inputs, and you build up some internal state as you go, of fixed size. You use that internal state to make your predictions. And the reason why this is good and nice is that it avoids what's in this block here, right? So at inference time, for standard transformers, in order to avoid recomputation, you build up a KV cache. And you can easily get into this situation here, where, say, for an 8 billion parameter model, Mamba 3 type, you have like 16 gigs of memory for the weights. And easily the cache, it can be much bigger. It's a huge cost. It also grows with the sequence length. These are all not good properties that we like to avoid. And Mamba does this by having a cache. There's also a cache you can use at inference time, but it doesn't grow sequence length. And it's also, you're not spending the time at inference shuttling this big cache, back and forth from HBM to on-chip memory. So you have better arithmetic intensity, better GPU utilization, better across the board. Also at inference time, it's constant time to generate the next token. You only have to reference this last state that you just generated. You don't have to scan back in time and do computation that grows with the sequence length, as you would in transformers. And so, as we've heard, long context, more and more important. You want to have the context of the whole code base. You want to process video, audio, time series. All these things are super blowing up the context length that we're interested in. Also, with the reasoning models, they're generating longer and longer context. So this is all positives. At training time, there's similar advantages. One trivial but important point is that these days inference is a subloop of training. Anything that's reinforcement learning, you're going to do generation. All the benefits of the previous slide carry over to training. So it's kind of a free win there. Again, they're parallelized in the sequence dimension. That's the main technical innovation, why Mamba is better than the RNNs of old. During training, you just have to scan once. And that means that during training, the computational complexity is linear in the sequence length. Again, that's different from attention, which is quadratic. Again, really good for long context. So for all the previous reasons, there has been a very popular trend of incorporating these Mamba layers into models. I'm again from IBM, so I'll highlight the Bamba model, which is the one up here. But there's a whole zoo of models of this form. These are all hybrid models. Usually don't use Mamba layers only. It's like a combination of the two. Maybe for every 7 Mamba layers, you'll have 1 full attention layer. That's kind of typical. Bamba in particular is a collaborative model built from IBM, collaborators at Urbana-Champaign, Princeton, CMU. And we see a lot of the promises of the previous slide realized. So at inference time, it's like 2.5 times faster than a comparable Llama 3 model. The latency is improved by a factor of 2 also. Theoretically, we could get this up to 5 with perfect engineering for the throughput, but already it's quite a bit better. The training, also very efficient. It's not quite as optimized as Llama 3, which has had more community work to optimize it, but it's within 20 to 30% throughput, and the model quality is quite good as well. I was talking about Bamba v1 here. Just last week, a v2 version was released. Just to advertise this quickly, it's just a further trained version of the Bamba model. And it works very well. By some metrics, it outperforms Llama 8 billion while using much less training data. Cool. So for the rest of the talk, I'll discuss the state of affairs of Mamba support in the PyTorch world and what IBM is doing to extend it and add advanced capabilities. Mamba's a new kid on the block. It doesn't have as much time to get as mature as full attention, but we're getting there. So I'll talk about, again, long context support, a theme I'll harp on again and again. Padding free training, which is a method for making supervised fine-tuning more efficient. I'll talk a bit about core torch ops, adding support for the things that Mamba needs, that Mamba's built on. And like many other people have discussed, make sure expert parallel support. And finally, I'll touch briefly on inference. So once again, long sequences, super important. And we want to be able to train our models on really long sequences in a scalable way. And the bottleneck when you do this is activation memory. So these are the tensors that you hold, that you generate, that you need to save to do the backwards pass to update your model. These grow with the sequence length. And the scalable way to do this is what's known as context parallelism. We heard this discussed nicely earlier today. But essentially, you have this long sequence, and you want to split it up in that sequence dimension. So GPU gets the first chunk of inputs, GPU on the next, and so on and so forth. A lot of things in the Mamba world live in this Mamba repo. This is by Albert Goon, Trudell, and friends, the originators of the Mamba model. And building on top of that, we have a quite performant context parallel implementation. That's what's in this plot here. So this shows the scaling. This is a log plot on the x-axis of training from 128K sequence length up to 2 million with a pretty good throughput profile. And there's no particular reason why I stopped at 2 million. I made this plot last week. That's the number of GPUs I could get, but you can scale up, add more GPUs, more context length. There's no growing memory limit to this. This plot is just for a stack of Mamba layers. One nice thing about Mamba layers is that, in principle, with perfect engineering, this will be a perfectly flat line. So for longer context, you have a constant tokens per second per GPU. That's not the case for a model with a full attention. So because attention grows quadratically, the best you could do in that case would be a curve that goes down like this, that gets worse as 1 over the sequence length. So just another manifestation of the advantage of these Mamba models for long sequences. Also true of any linear attention mechanism. So next, I'll talk about padding-free supervised fine-tuning. So this is, we heard a bit about this in the NVIDIA talk. So this is where you use really high-quality data to teach your model to be more useful, to follow instructions. You know, this is where you introduce the tags for system, user, assistant, this kind of thing. And this is really high-quality data. You want to use it as well as you possibly can. One thing you want to do is not have different examples bleed into each other. So during pre-training, the step before this, the examples are less well separated. But here, you really want to use it the data as best as you can. So the naive way to do so is to just batch things together, right? So you have 3 different sequences combined in different batches so that they're treated independently. To do this, though, you'd have to add padding, and padding is not great. It's wasted compute, wasted memory, even though you're effectively ignoring these circuit out bits in some ways. You know, they still are a cost. And so what's better to do is what's known as padding-free training, padding-free concatenation, where you instead, you just concatenate them together, have a little more information telling you where the boundaries are, and write essentially specialized kernels so that you don't attend to different examples. The kernels are really most of the hard work. Fortunately, TreeDown and friends already have that capability in this Mamba repo. What IBM has been doing is essentially connecting the pipes and making this available in Hugging Face. So it's very easy to use. And the improvements, they depend on a few things like your particular training setup, your data distribution, how the variance in the sequence lengths, because the advantage is from cutting out the padding. But we see typically a 2x improvement in throughput for supervised fine-tuning. So it's really quite a good return on investment here. And again, this is being streamed to Hugging Face. So at the PyTorch level, the core PyTorch level, we have a few efforts going on there to have better support for Mamba operations. One is, I've talked about the scan a few times. Mathematically, it's something called an associative scan. But today, the way it's implemented in the Mamba repo, say, it's a bunch of Triton kernels. They're great, super high performing, but they're not easy to hack on. They're not easy to change. They don't have the nice benefits of, say, PyTorch eager mode. And so one line of work is in, producing a associative scan op, a native operation in PyTorch that will let you, re-implement Mamba, try your own thing, hack on these kinds of models and experiment. The dream is to have this be primitive that's similar to scale.product attention. So this would be the scan version of that. Another area of PyTorch that we are contributing to is the detensor API. So for those of you not familiar, detensor is PyTorch's native sharding API. So if you have your model and say you want to do tensor parallel on it, you can do this with just a few API calls, and Torch converts your tensors to sharded tensors, these detensors, and it'll just work. It's quite nice. But it requires some special things. So the operations that you perform on these detensors, they're not the same logic as what you perform on a not sharded tensor. It has different dispatching, so you need more work there. And so some work in progress is to have support for the kind of operations we're doing in these Mamba models. So not only is there a scan, there's also some convolutions in the sequence dimension, and just making sure that this has first-class support in detensor is a work in progress. We've also heard a few times now about mixed shared experts. I won't go into too much detail about this, except to say that they're, instead of one MLP layer, you have a bunch, effectively. And in order to train these models that have these layers well, you want to, one way to do it is to put different experts on different ranks. So you have GPU 0 gets some chunk of the experts, GPU 1 gets the next chunk, so on and so forth. That just lets you have enough memory on each GPU to actually train these things. And then you have like communication between these ranks to do the right computation. And so we are working on providing first-class support in the Mamba repo for this kind of sharding setup to make it easy to train MOE Mamba models. On this note, just this last week, a little less than a week ago now, IBM also announced a preview of their next generation Granite models, Granite 4.0, tiny version. And these are hybrid MOE models. So they involve some Mamba layers, some attention layers, and MOE additionally. This one's, again, as the name suggests, a pretty small model. It has about 8 billion parameters or so. It's still being trained as we speak, but the results so far are quite good. Prompted IBM to release an early checkpoint already. Clearly, we're quite excited about this work. If you're interested, you can check out the checkpoints on Hugging Face. And last, this could be a whole talk in itself. I'll cover the inference part, so we heard from the VLLM team earlier today. I tend to focus on the training myself, so I'm only this one slide on inference. But there's a huge effort at IBM supporting VLLM and to give first-class support to the Bamba model and Mamba models in general. So, my excellent colleague Fabian added the Bamba model in February, and so right now tensor parallelism is supported for Bamba, and there's more advanced work in supporting advanced features. So, like one, the Mamba cache, like we talked about, it's quite different from the KV cache of transformers models. And we're working on like a general solution that can quite flexibly accommodate all kinds of caches that we want now and in the future. There's also chunked prefill, which is a technique for having better GPU utilization, saving money while serving your models. And then, as always, we're working on faster training kernels, trying to get that 2.5x speed up in throughput up to as close as we can to the 5x that we think we can get to. That is most of what I wanted to say. I'll leave you with a few links here to the various blog posts about the models, their announcements. There's another Hugging Face blog post about the padding-free work, the data collation to make it easy to do that padding-free training. And you're also just welcome to contact me. Thank you all.
Thank you, Garrett. Do we have any questions?